3, 2, 1.
Being unstable.
You may be surprised by the strange thing presented before you now, but let me tell you what, this thing is one of the most important achievements in the history of humanity. This thing is called the particle accelerator. Particle accelerators are devices that speed up and increase the energy of a beam of particles by generating electric fields that accelerate the particles and magnetic fields that steer and focus them. They were invented in the 1930s to provide energetic particles to investigate the structure of the atomic nucleus and have since been used to investigate many aspects of particle physics. Particle accelerators use electric fields to speed up and increase the energy of a beam of particles, which are steered and focused by magnetic fields. The particle source provides the particles, such as protons or electrons, that are to be accelerated. The beam of particles travels inside a vacuum in the metal beam pipe. The vacuum is crucial to maintaining an air and dust-free environment for the beam of particles to travel unobstructed. Electric fields spaced around the accelerator switch from positive to negative at a given frequency, creating radio waves that accelerate particles in bunches. Particles can be directed at a fixed target, such as a thin piece of metal foil, or two beams of particles can be collided. Particle detectors record and reveal the particles and radiation that are produced by the collision between a beam of particles and the target. Types of particle accelerators. There are two basic types of particle accelerators, linear accelerators and circular accelerators. Linear accelerators propel particles along a linear, or straight, beamline, while circular accelerators propel particles around a circular track. Linear accelerators are used for fixed target experiments, whereas circular accelerators can be used for both colliding beam and fixed target experiments. Particle colliders are a type of circular accelerator that collide two beams of particles head-on. The Large Hadron Collider, LHC, is an example of a particle collider that accelerates and collides protons and heavy lead ions. Particle accelerators are used in a wide variety of applications, including fundamental research, medical diagnostics and therapy, semiconductor manufacturing, and environmental monitoring. Electrostatic accelerators, such as the Cockcroft-Walton accelerator and the Van de Graaff accelerator, use electric fields that do not change with time to accelerate particles. Oscillating field accelerators, such as linear accelerators, LINX, and circular accelerators, use oscillating electric fields to accelerate particles to extremely high energies. Particle detectors record and reveal the particles and radiation that are produced by the collision between a beam of particles and the target. Components and functioning. We have four main components common to all particle accelerators. First, sources of particles. Sources of particles for particle accelerators can vary depending on the type of particle accelerator and the experiment being conducted. Hydrogen gas is a common source of particles for many accelerators. Physicists can strip electrons from hydrogen gas using a duoplasmatron to produce protons, which can then be accelerated. Other sources of particles include ion sources, which can produce ions of various elements, and electron guns, which can produce beams of electrons. Some accelerators use radioactive isotopes as a source of particles. For example, the spallation neutron source at Oak Ridge National Laboratory uses a target made of heavy metal to produce neutrons through the process of spallation. The type of particle used depends on the aim of the experiment. Linear accelerators typically use electrons, while circular accelerators can use protons, heavy ions, or electrons. Particle colliders, such as the Large Hadron Collider, LHC, collide two beams of particles head-on and typically use protons or heavy ions. Second, methods of acceleration. Particle accelerators use electromagnetic fields to accelerate and steer particles. There are various methods and mechanisms involved in the acceleration process, including the use of radio frequency cavities and magnets. Electromagnetic fields. Particle accelerators use electromagnetic fields to propel charged particles to very high speeds and energies, and to contain them in well-defined beams. These fields are generated by specially designed metallic chambers, such as radio frequency, RF, cavities, which are spaced at intervals along the accelerator. These cavities are shaped to resonate at specific frequencies, allowing radio waves to interact with passing particle bunches. Each time a beam passes the electric field in an RF cavity, some of the energy from the radio waves is transferred to the particles, nudging them forwards. Magnetic fields. Magnets play a crucial role in focusing and steering the particle beams. Dipole magnets bend the path of a beam of particles that would otherwise travel in a straight line. The more energy a particle has, the greater the magnetic field needed to bend its path. Quadrupole magnets act like lenses to focus a beam. In linear accelerators, the particles travel in straight lines, accelerated by the electric fields along their paths. In cyclic accelerators, magnets are used to steer and focus the particles as they travel around a circular track. These accelerators use oscillating electric fields to accelerate particles to extremely high energy. These methods and mechanisms are essential for the functioning of particle accelerators, allowing scientists to study particles and the forces that shape them, and to investigate many aspects of particle physics. Third, detection and measurement tools. As we know, particle accelerators are used to accelerate particles to high energies and then analyze and measure them using different instruments and detectors. The primary method used to measure elementary particles is to produce these particles in high-energy collisions and then measure the products using highly sensitive particle detectors. These reagents are used to test and revise scientific models of particle interactions and are essential to experimental particle physics. Some of the instruments and detectors used to analyze and measure particles accelerated in particle accelerators include particle detectors, used to measure the products of high-energy collisions between particles. They are designed to identify and measure the properties of particles produced in these collisions. Examples of particle detectors include drift chambers, time drop chambers, calorimeters, and tracer detector. Computational tools. Computational tools are used to design and analyze accelerators. These tools help simulate and model the behavior of particles inside the accelerator, as well as the performance of the accelerator itself. They are essential for improving the design and operation of particle accelerators. Particle accelerators and their associated instruments and detectors play a crucial role in advancing our understanding of particle physics and the fundamental forces of nature. They are used in a wide range of scientific research and have contributed to many discoveries in the field of particle physics. Fourth, vacuum systems. Maintaining a vacuum environment inside particle accelerators is crucial for several reasons. Minimizing beam-gas interactions. The vacuum environment minimizes beam-gas interactions, ensuring that the accelerated particles can travel unobstructed through the accelerator without colliding with gas molecules. When particles collide with gas molecules, they can lose energy, reducing their intensity and lifetime. Preventing energy loss. In a vacuum, charged particle beams can travel without losing energy due to interactions with gas molecules. This is essential for maintaining the energy and intensity of the accelerated particles. Optimizing performance and reliability. Vacuum systems and particle accelerators must be able to deal with a wide range of complex instrumentation and radiation issues while keeping operation and maintenance costs under control. They must also address radiation issues that can impact performance and reliability, such as modifying the mechanical and chemical characteristics of the materials in the vacuum system and increasing their radioactivity level. Beam lifetime. The goal of vacuum design is to achieve a pressure level such that beam lifetime due to residual gas scattering is significantly below certain thresholds, such as the 2-check lifetime, which can dominate in certain conditions. Achieving and maintaining the appropriate vacuum level is crucial for optimizing beam lifetime and minimizing beam loss due to residual gas scattering. In summary, maintaining a vacuum environment inside particle accelerators is essential for minimizing beam gas interactions, preventing energy loss, optimizing performance and reliability, and maximizing beam lifetime. This is critical for the successful operation and scientific outcomes of particle accelerators. Applications in scientific research and industry. Particle accelerators are involved in many fields, but we will focus on the most important ones. First, particle physics. Accelerators help in understanding the nature of matter and the universe by accelerating particles to very high speeds and then analyzing and measuring them using different instruments and devices. These instruments and devices are used to measure the properties of particles produced in high-energy collisions between particles. These tools help test and modify scientific models of particle interactions and are fundamental to experimental particle physics. Second, materials science. Particle accelerators can also contribute to the study and development of new materials in data science. For example, data science accelerators can use data and machine learning to predictively design new materials. In addition, particle accelerators can be used to gain insights into the structure and function of materials at and below the atomic scale, allowing scientists to study the properties and behavior of materials. By examining the internal structure of materials, scientists can develop new materials for industrial and medical applications. Particle accelerators can also be used to study the behavior of materials under extreme conditions, such as those found in nuclear reactors, and to develop new materials that can withstand these conditions. Third, medicine and healthcare. Particle accelerators are widely used in the medical field, and their uses include curing cancer. Particle accelerators, especially in the form of proton therapy, have become an important tool in cancer treatment. Proton therapy uses particle accelerators to deliver high-energy protons to cancerous tumors, offering several advantages over traditional radiotherapy. The physical properties of high-energy protons allow radiation to be deposited more targeted than X-rays, reducing toxic radiation doses to healthy tissue near the tumor and reducing side effects of treatment. Proton therapy is used to treat a variety of cancers, including brain tumors, spinal cord tumors, head and neck cancer, lung cancer, liver cancer, pancreatic cancer, prostate cancer, sarcomas, and others. Proton delivery technology continues to advance, with the development of intensity-modulated proton therapy, IMPT, allowing unprecedented control of the treatment beam. This method provides control of the intensity and position of the proton beam, allowing more precise treatment. Overall, particle accelerators, especially in the form of proton therapy, have revolutionized cancer treatment by offering a more targeted and precise way to deliver radiation to tumors, thus minimizing the impact on healthy tissue and reducing the side effects of treatment. Medical imaging. Particle accelerators play a crucial role in medical imaging technologies. They are used in many medical applications, including positron emission tomography, PET, and the development of new imaging techniques. For example, a positron emission tomography scan involves introducing a radioactive isotope into the body, which emits positrons. The resulting gamma rays are detected by a PET scanner, providing information about body function and metabolism. In addition, a new medical imaging technology called proton computed tomography, PCT, which uses protons instead of X-rays, is also being developed. This technology aims to reduce the patient's exposure to harmful radiation while producing 3D images that are more accurate than those produced by current CT scans. Particle accelerators are essential in medical imaging techniques and cancer treatment, and play an important role in positron emission tomography and the development of new imaging techniques. Its applications in medicine contribute to advances in diagnosis and treatment and the development of innovative medical imaging techniques. Construction risks and challenges. Particle accelerators face multiple challenges in their construction and operation, including cost. Building and operating particle accelerators requires advanced technology and significant financial investments. This includes ongoing maintenance and operating costs and ongoing technology updates. Technical challenges. Designing and building particle accelerators poses complex engineering and technical challenges due to the extreme necessity of precision and stability in particle acceleration and guidance. Energy and the environment. particle accelerators consume large amounts of energy and generate large amounts of heat and radiation. This requires solutions to manage energy and environmental impacts. Safety and security. The safety of workers and the environment surrounding the accelerators must be ensured, and strict safety procedures must be provided to prevent accidents and radiation leaks. Research and development. Developing new technologies and improving performance and efficiency requires investment in ongoing research and development. Despite these challenges, particle accelerators play a vital role in scientific research and advanced technology, and contribute to expanding our understanding of the universe and matter and their applications in important fields such as medicine, energy, and the environment, as we mentioned. Conclusion. At the conclusion of this video, we all realize the great impact that particle accelerators play in achieving tremendous progress in several scientific fields. From examining the fundamental nature of matter to techniques for analyzing materials and treating diseases, this technology is proving more and more over time that it is not just a scientific research tool but a vital partner in developing our future. When we highlight the achievements of particle accelerators such as the Large Hadron Laboratory, LHC, and their contributions to our understanding of the universe in which we live, we see that we have entered an era of discovery and interaction between advanced sciences. Despite the technological challenges, the future of particle accelerators looks promising, as they are expected to continue inspiring researchers and engineers to push boundaries and reach new levels of understanding and innovation. In the end, we express our gratitude to those accelerators that have greatly contributed to improving our lives and expanding the horizon of our knowledge. It is a continuous journey towards a future that relies on innovation and technology to achieve limitless achievements.